And the next speaker is Aliwen Delgado from the Catholic University of Chile. He will be talking about the KaiKai detector, deep underwater geoscience of neutrinos plus supernova triangulation.
You have to mute.
Sorry, I was muted. Hello, everybody. Are you listening to me?
Yes, it's okay. We hear you.
Oh, sorry. Well, my talk will be a little bit different. I will be talking about neutrinos detection with experimental approach. So the first question this study want to answer was where to place a new detector, considering that the solar neutrinos are well as reactor neutrinos and atmospheric ones are well studied, and in the future, accelerator neutrinos, as well as double beta decay experiments, want to answer the nature of or investigate the pure nature of neutrinos. So I began to think about another kind of experiment that ones relate supernovas. Supernovas are quite interesting for astronomy, but for nuclear physics and particle physics as well. It's interesting because in the process of a core collapse supernova, the first particle that release the place are neutrinos. So here in Earth, the first wave of particles will be neutrinos even before light or other particles like protons or extremely high gamma rays. So that brings us the possibility to triangulate with neutrinos the place in the sky where the supernova will be could be seen in light. In the current state of neutrino detectors, there is a collaboration called SNEWS, Supernova Early Warning System, that bring Diabase, Super Kamikande, Cumberland, Snowblood, Barrexino, and Ice Cube united and try to, in the event, on the hypothetical event of a supernova, will try to triangulate and tell the astronomy community where will be this supernova in the electromagnetic range. So taking account that the distance between those detectors in the world is the main feature to maximize, I try to answer the question where to place a new detector, trying to maximize the distance to current detectors. So this map shows the worst and best place to place a new detector in order to maximize the triangulation. Naturally, the worst place will be putting another detector in Asia because Japan have Super Kamigande and Kamala, and China have this in Diabase. So the best one, the best place will be South America, the other corner of the world, especially the Pacific Ocean. And taking this analysis one step further, uh, considering the number of events in case of a supernova and future detectors like Jimpin, Hyper Kamiokande, or CAMNET in Europe, the optimal place move to further in the ocean, nearer to Eastern Iceland, in those coordinates in the South Pacific Ocean. So, where to place a new detector for triangulation of supernovas? In the middle of the ocean. That it's a quite a strange idea, maybe for some of you, but the uh, the proposition of neutrino detection in the ocean is not new. Deep ocean neutrino detection have been proposed more than 10 years ago by Hano Hano, a deep ocean anti-neutrino detector that was think first for geoneutrino science. And this idea have been developed since then. And now it's called ocean bottom detector. Then the main objective of this ocean bottom detector is still geoneutrinos. Why geoneutrinos? Well, geoneutrinos are the neutrinos coming from the Earth, the mantle and the crust of the Earth, from several radioactive elements, mainly from uranium and thorium, but from potassium, rubidium, lanthanum, ruthenium, and so on, many others. That in the process of beta decaying, those elements liberate energy, so that heat liberated in the mantle help to preserve the mantle convection as well as the dynamo inside the Earth. So it could be correlate those geoneutrinos to even the magnetic field of the Earth. That's why geoneutrinos are quite interesting. And in an analogy, the same potassium that makes the Earth radioactive is that make bananas radioactive. The neutrinos in the past have been detected by two experiments, Hamelin in Japan and Boraxino in Italy. But the places where those are sited are way near to nuclear reactors. So that it's not optimal because nuclear reactors are a kind of irreducible noise for geoneutrinos detection. That brings us to the computation of the hypothetical detection of geoneutrinos here in this optimal place in the middle of the ocean. And this study used the crust one and prime models of the mantle and the crust of the Earth with different layers, different thickness, and different enrichment of radioactive elements, taking all of that in account. And with this approach to approximate the geoneutrino flux, uh, the result of that computation is this graphic here, this map on the left, that shows in the optimal place for triangulation, the main contribution of the crust came from the nearer places. So the middle of the ocean, the crust in that place is thin, but if you move further to the American continent, you will see more geoneutrinos coming from the Andes mountain. So you can say in a way you will see less mantle geoneutrinos. The noise in those oceanic sites will be hugely suppressed by the amount of water above you. So the deepness of your experiment is the main variable here. As you can see in this approximation for muons as well as for neutrons, the deepness is the desired or the most advantaged variable. As well, when you put your detector more in the deep of the ocean, it will be it will have a lot of pressure there. And in this optimal zone of triangulation of supernovas, there's an interesting place, the Atacama Trench, that have a deepness of 8 kilometers. So in the past, some oceanic scientists from Chile and USA have reached this 8 kilometers deep with a lander, Audacia lander. That way, we can think which will be the signal in the optimal place for triangulation as well as the signal in the Atacama Trench. This is the computation for the optimal triangulation place near from the eastern ice line, as I was saying. You can see here that the mantle will be at low energies, 1 megaelectron volt, 2 megaelectron volts, and the cross, mantle and cross, will be the huge proportion of the signal. And the nuclear reactor neutrinos as a noise will be suppressed because in South America, we have only two reactor neutrinos, one in Brazil and one in Argentina, quite far away from this place. How you will detect, or how could you possible detect these geoneutrinos? Well, Hano and Ocean Bottom Detector have proposed the technology of liquid scintillator, quite common in the world, that have a problem here because it's necessary a neutrino above 1.8 mega electron volt of energy to make a signal, a photon in the inverse beta decay process. The other technology used in the current and the future detectors is a solid state one, which where neutrinos interact in a scattering of nucleus or electrons, and that neutral current channel uh, make available to see all the flavors of neutrinos. So it's a better approach, I think. And in that way, using those two technologies, I idealized a detector with 10 kilotons of mass, diffusion mass, 1 year of exposure, 100% efficiency because it's an ideal situation, and taking in account the cross section of the different interaction and the flux and the distribution of energy of flux of geoneutrinos. So in comparison, solid state detectors will have a huge number of events, and the low energy regime, 1 mega electron volt, 2 mega electron volt, that kind of technology will see those geoneutrinos coming from potassium, coming from rubidio, coming from lantano, all of those elements that liquid scintillators not can see. So liquid scintillators from the limitation of the threshold only can see the uranium and thorium lines of decay. To summarize, I propose KaiKai, a solid-state aquatic detector, planned as a portable instrument operable in the deeps that is expected to measure geoneutrinos from the mantle up to 80% of the signal. The current location, as well as the future location of the neutrino detection detectors, shows that the Pacific Ocean is an optimal place, a wide zone of optimal triangulation of supernovas. And in this zone, the Atacama Trench presents higher standards of low radiation than underground laboratories because it's quite deep. The comparison of those two technologies, liquid scintillator and solid state detectors, its different interaction, the volume, the energy, observation, all of that supports that KaiKai will will be or would be a solid state detector. Similar as this shown here, Audacia lander. Well, Audacia is a oceanographic experiment, but in that technology, in that approach, different from Hano or ocean bottom detector. The conclusion of that study is that the Pacific Ocean is perfect to achieve both geoneutrinos detection and supernova triangulation. And on the other hand, the development of a solid state aquatic detector will be of huge scientific importance in the world are being studying these possibilities. Thank you very much.
Thank you for the nice presentation. Are there any questions? Yes, Mauro.
Yes, thank you, Aliwen, for your talk. I enjoyed it very much. My question is a bit off topic. It's related to sweet underground water. Do you know if similar techniques can be used to find these huge reservoirs of underground water? Because we know sweet water is, we are in desperate need for that. So
yes, the Japanese company that support the ocean bottom detector try to achieve a lot of things at the same time. One is the mantle drilling, so there is a mining purpose of the project. One is the agua pesada, the
heavy water.
Yeah, heavy water, sorry. Heavy water, and one is those pocket of sweet water in the bottom of the ocean. So it's a more complex project than all the geoneutrinos, but yes, they are trying that.
Thanks.
Okay, the next question, Claudio Deep.
Yes, I have a question about the background you will get if you try to get geoneutrinos from the mantle, and well, the typical geophysics models say that most of the uranium or so are in the crust. So the typical experiments, like what you mentioned, Borexino or so, they try to subtract the radiation from the crust by measuring in different sites around, like 500 kilometers around the place. Well, you won't be able to do that if you're under the ocean. So how do you estimate the radiation from the crust? You suppose that the amount of material in the crust under the ocean is similar to the one you have on the surface. Is that how you do it? Or you have detectors that you have directionality for the neutrinos?
No, there is no directionality, but oceanographic studies of the crust have already done across all the world. So yes, you don't have the precise characterization of the elements in that part of the ocean, but you can infer that it's quite similar from, I don't know, 100 or 1,000 kilometers north and south. So it's like a guess, but it's not a rude guess. It's more like a question.
Yes, and you make an estimate of the thickness of the crust under the ocean.
Yes, yes, but the thickness is better understood because seismic waves tell us which is the thick.
Now, if you go in this Atacama Trench there, then I'm concerned with the geometry, because you're like in like in a cliff there, so you have earth from all sides, so that could be more difficult to estimate there the background maybe or something, no?
Yes, there will be more difficult, but as well, the Nazca plate and the American plate are well studied in the richness of the radioactive elements. So you could make a valid guess, but the shielding that you will get from those crust from external sources will be better. So in a way, it will be a more noise from the surrounding, but less noise from the other places.
Okay, thank you.